Well, okay. I'm just gonna casually do more of the same today. That's the rule for my rule. That's the name of the game today. Casual coding, getting things lined up and in order. I've also been capturing some notes for a video series related to some sort of beginner-friendly informational videos, I guess you could call them. They're not quite, I guess they are tutorials, but they're more like how to use Clojure kinds of videos. That's the idea. Because I feel like I'm a decent explainer of concepts and I want to start making some of those videos again. But some of the name of the game today is a little less focused on this sort of thing. So I'm going to actually hide that. Well, hide it. I'm not going to hide it. I just don't need it open right now. I'm going to work on SVG and Forge because I want to start pulling this data, these functions from my pottery namespace into their proper places. That's the name of the game today. And I'm just going to have some fun with that. So that's what's up. We're just gonna make sure. Yeah, okay, things look good. All right. So, I've been trying to wrap my head around a few things, actually. And one of those things is, well, sorry, I gotta check this for a second. Okay, right, back to work. Okay, so the stuff I was trying to think about here. If I go, parametric is kind of the area of focus I've been working on for creating cool 2D and 3D geometry. That's kind of, it's been a lot of fun, and been thinking really hard about this sort of thing. One of the slow things is this here. And I want to figure out if there's a way where I can speed things up. That's what I want to do. I think this is valid. So let's see here. If I do R map, right, it does. How does this work? Reduce that reducer into 0? I'm not sure I understand. Oh, I'm being silly, of course. A little bit silly anyway. Let's map ink to this. Oops. Okay, that does what I think, or what I thought. Okay, r/reduce. Let's take the function rmap_ink. I don't think I'm doing this correctly. Collection. Does this have to be like this? I'm trying to replace this with something that could be faster. That's the whole idea. Because what I want to do is, well, okay, let's def a, well wait, what is a, first of all? It's a bezier. Okay, so, right? Yeah, it's a bezier. Alright, so what I want to do is, arc length of A, right, has this timing to it. Okay, so if I time arc length A, I want to see if I can reduce this. So it takes 2 seconds to approximate the arc length at this delta. It goes way up, like it can go way faster if I make this a bigger number, but the accuracy starts to fall, which is not what I want. So I want this to be under 1 second. I think I want it to be under half a second if I can get it to do that. So, you know, I've got to figure out how to do that, really. So I want to map curve over this range. The range itself is fine. This here first of all, let me just see if I do something like that. That doesn't automatically speed it up. I'm sure it doesn't. Yeah, we're getting in the same range of time. So that's just not helpful. Really, it's not what we need. I feel like there's something related to things like reducers and or transducers in Clojure that I have to, these are pretty fundamental that I have to understand, and I'm just not quite there in terms of getting the concept in my brain. So we're gonna fiddle around with it a bit, and then we're also going to figure out this here, right? This is the slow part. Let me check, first of all. If I go utils distance, here, what we have here is square root issue. And by issue, I just mean it's the square root. The square root is slow. Well, that's just the reality of it. It's just not good. Let's make a little function that's just the square distance. It's just reduce plus v star let v minus ba. Oops, that's the wrong namespace, but okay. Alright, so we got that. I don't know if that'll be useful, but let's table that anyway. Let's do the super naive thing that I'm almost certain is actually just wrong. Let's do... Well, first of all, okay, let's zip on down to here. Let's do... let's make an intermediate function here. So arc length proto. Okay. The map v didn't help, it actually slowed it down, so let's get rid of that change, make sure that's not in there. We have to figure out how to use our map. That alone might be a good speed up, but let's figure that out first of all. We also need to do this. We need to make sure that we're calling the correct functions. Okay. This is not going to work because I have to reload the file source svg clj utils. Okay. Right, so if I do time arc length proto, it's going to give the wrong answer. It's also not very fast, so that didn't really change anything. I'll be honest, I'm a bit surprised by that. Is it always the case that square root of a decimal is bigger? Yes, that is necessarily true, because anytime you multiply a decimal by, if you multiply any number by a decimal value less than 1, it's going to reduce the size of it. It's like a scaling down of the magnitude. That's always going to be true. Therefore, the square root of a decimal value less than 1 is actually going to be bigger than the input of that square root call. So this pattern makes perfect sense. And of course, we're going to get a smaller value for the distance. And then of course, right, if we were to just, first of all, let's time it again, right? And then we just do mass square root of that value. It's obviously not even close to the true distance, because the true distance, well, the truer distance is 200 and something. So you obviously cannot just do the squared distance. That's just not practical. But that's also clearly not the element of this function that's giving us this, that's not the real bottleneck. Because if we look at, and these are really rough numbers, they're not going to be accurate because you need to do this for all kinds of different things. I'm just using it as a starting point, really. This isn't really good profiling. You'd want a more robust testing approach, you know, kind of exercise the function in multiple cases and do average timings and stuff. This is just better than nothing. It's an order of magnitude argument for myself to kind of, let me see if I'm on the right track. And if we look here, right, sorry, the wrong one. Here, we're in the same ballpark as as using the proper distance calculation. So that's really not going to be anything we need. Right. So what we'll figure out instead is how to use the reducers library. That's what I want. Okay, so let's go fold. Let's look up fold and see what's up here. So we're in the Clojure core reducers. Okay, that's what I want. Okay, well, first of all, let's see if I even get the right idea here. So the reduce function, let's assume it's plus, okay? And let's just do range 20. Okay. Yeah. Okay, we're on the right track here. Let's also just do regular reduce. Now we're getting huge numbers, which is not at all surprising. Might have been bold of me to make a number that big, but okay. It should hopefully not blow up my, should hopefully not run out of memory, but I mean, I guess really all I'm trying to do here is understand the reducers library enough to try use it. Integer overflow. Yeah, cool. right. Let's get this number a little smaller here. There we go. Okay. Right. So now let's do this and time it. .7 seconds. Let's see. It took longer. Great. Took longer. Okay. Love it. All right. Well, let's not panic yet. Let's see. Maybe we could still get this working in a sensible way. Okay. Seems plausible. And the other thing is the Bezier implementation itself here. Uses a bunch of lines in a recursive approach. And requires interestingly enough let me see this. Def B, fastline. Okay. B0 works. B1 should also work. Okay, good. We're in the right. We've got the right idea. The thing about fastline is I should be able to use that internally here, like this. So what I actually want to do okay, they both work. That'll be fine, I think, really, because what I can do, yes, I think this is what I'll do. First of all, let's do that. The reason I'm doing this is because it eliminates a distance calculation. Yeah, and it doesn't matter because I don't need it. I'm basically discarding everything else. Yeah, I think that's actually a good idea. Suppose we'll find out, really. Oops, that's not at all what I wanted to do. I want to do this, please. There we go. Ooh. Interesting. Okay, so that actually sped things up a ton. Look at that. Eliminate the distance calculations for any intermediate line process, and we actually still get the right answer. That's... okay. That's pretty awesome. Okay. I like the idea of this. And let's actually make it public, because this exact optimization could be super useful for other internal processes. So here, let's see, right? If I do... okay, so here we're a little bit... yeah. Right. In the case of polyline and polygon, it kind of makes sense to still have a proper line called there, because we're not recalculating the distance between points at all, because we are required to draw those lines anyway. They're calculating their distances and then we're summing them up. It'll either happen as you generate each line or as you generate the polyline itself. So it might be faster to do fastline and then build a proper, like, build a better reduce pipeline, although I'm gonna leave that one for now. But let me put a little note here. Line is a very simple parametric curve, but is used a lot in other contexts. Especially because it can build some very useful interpolations for you to make certain circumstances faster when the line's length is irrelevant. A user or other function with lines internally You know what? Why do I put this in a parenthetical? Example, Bezier. Fastline can be used to avoid calculating length at all. This speeds things up because a line's length uses math square root, which is fast enough but slows down when doing lots of calculations. Right, so this was observed to have noticeable improvement on estimating arc length of a Bezier curve, since lines are created for any t. Avoiding length calculations is critical as the lines generated depend and on the order of the Bezier curve. More recursion for higher order Bezier curves. Blah, blah, blah. This is already a big improvement, which I'm happy with. Let's also have a quick look at this. Let me make sure. Because here, we're kind of boxing things up again, and I wonder if I could make that even faster. Or we're not like we're I suppose we should actually check that I'm doing it right. Let's pop into here, I guess. Do deafen, show, parametric, curve F is just going to be tools. Well, first of all, let's just do let points be map F over range 0 to 1. Let's do 100 points as a useful amount of points, really. And then we'll map points, or thread, sorry, points through closed is just going to be equals F0. Oh, sorry, no. We'll do it the EPS way. EPS is 0.00005 is fine for me. Let's do utils distance Does that work? Yeah, that should be fine. F0, F1 is less than EPS, then it is closed, otherwise it's open. Right, so all we need to do is the draw function is if closed, then it's polygon, otherwise it's polyline. Right, so we just do draw draw a function over the points, simple enough. Transform style. Let's do fill, none, stroke, lime green. It's probably one word, yeah. And then stroke width 3. And I think that should work. Oh, except I want to then do tools/cider show automatically in there. So let's do that. So let's try show parametric A. Good, I think. Right, so let's redef A because it's a little boring. Let's pop a minus in there. Okay, that seems to be working, which is nice. So let's do pathbezier. We just want to make sure that it is rendering the same way. Oops. Oh. So let's take that, thread it through tf/style, fill, none, stroke, white. That is the same shape. We get the wrong bounding box from it, but that's something we'll deal with another time. That's definitely the same curve shape, so I'm happy that the fastline implementation is working the same way. That's really what I'm trying to get at here. Okay. Okay, so that is pretty good. I'm gonna be happy with that for the time being. Let's go back into this namespace here. And I'll be right back. Alright, back at it. Okay. Wait, is this actually correct? This range, let's first of all I might need to actually fix this range up. Right, so let's, oh, I'm in the wrong namespace. Okay, so we know a line, oops, let's def a line, right, is going to be p line 0, 0, 100, 0. So we know the length of this. Oops, I'm doing the thing again. Okay, so we know that a line's distance is exactly 100 because it's just 100 units along the x. So if we do arc and it gives us a wrong, so here we are, see? This is wrong. So if I do TATB instead, let's see if that's correct. Yeah, so we've got this particular, let's think about this for a minute. Let's imagine the step count. So the range has to be from 0 or from TA to TB and the step size is 1 over segment. And this is going to take a ton of time because there's a ton of segments that it's doing, right? And that's not exactly what I want. Let me think about this. This should work. It's a little... I don't know that it's actually smart, though. That's the thing. Oops, I also did this wrong. Let's also just bring this a little more sane number here. Let's start like this. Let's do this at least. Okay. Let me also do this. Last in range, last that. Yeah, so okay, so this is what I don't want. There we go. That's way closer to what I want. Okay. I think that that's correct. That gets us start. And it gets us exactly the correct range that we want. Then if I round, yeah, I think that's correct. So that actually gets us a more accurate number, which is pretty important. So if I do this, set, oh. Okay, and then I kind of think I should round to 5. Oops. Oh. Oh. I don't know if I like that design. But doesn't really matter. To be honest, it's not that big of a deal. Although, let me see here. Is that gonna work the way I think it is? Did this wrong. Huh. Let's try this. Okay, that makes sense. I think that actually slowed it down though, so let's get rid of that idea. Right, so here's what the thing that's happening here is the distance, it's calculating everything and then rounding everything right away because, yeah, okay, that makes sense. So let's just pop that all out of there. At least it works, so the machinery of the rounding, binding, and all that works pretty much the way I want it to. The reason it was saying 0 is because it was rounding every single distance calculation to 0 or 2 decimal places, but each distance is less than that because the step size is super small. So it was just all the values were disappearing through the rounding process. So we won't use that there. I mean, if anything, we should use rounding at the end. And then we can... Let's just hard code it in there for now. Although technically, like, the correct way to do it to allow the user to specify it, right, is just call it without an argument to the numbers place. But anyway, I think that should work, right? No such var utils / rounding. Round. There we go. Okay, so this arc length of this line should be exactly 100. Yes. Okay. That's pretty good. Seems good to me, honestly. That's probably not going to be the spot that's slow anyway, so I'm not really concerned with that. Alright, let's do that into here now. So we've got the same thing for arc length proto. Okay, so let's time, oops, gotta do this. Right, so that's slow, right? I don't love that, but okay, so it is. If A is still the Bezier, right? Okay, so let's now start timing the Bezier. Ooh, I don't love that. I thought I defined Bezier A. Ooh, I thought that I had sorted this out. Might not be true. Yeah. This should be the fastline Bezier. Ooh, that's not good. I mean, I don't love it, is really the truth here. Let's check. Maybe I was wrong. Well, maybe I'm wrong about everything. It's very possible. Okay. Let's just get rid of the rounding here first, okay? How about that? Okay, so that's not appreciably slower, which is good. Oh, okay, you know what did get slower? Although, here's what's happening. My segment size before was a delta value that was actually... Oh shoot, I should of course... I changed my step size to be a lot smaller, so the total calculation time increased. But but did the accuracy, like what accuracy gains am I getting here? Look at that. See that? Massive speed up, and to 4 to 5 decimal place. It's the same to like 7 or 8 decimal places. So let's pop this rounding back in here. And let's easily make that change like this. That's really good. So let's sanity check here, right? If we use a line, it's quick and ooh, the round, did the rounding break? What have I done? Oh, that's right, I turned rounding off. There we go. 70 milliseconds for, as far as I'm concerned, exact answer. We know in this case, a line is exactly, it's a horizontal line, 100 units long. That's by definition, so it's guaranteed. I know the exact length, and our length estimator is calculating the exact length. So our segment step size here is pretty darn good, I gotta say. Let me check this though. Probably, okay, so it's 7. See right, if I def a line to be a line from, okay, let's do something like this. Let's do -500 0 500 0. Okay, so the length of it is going to be 1,000. It's going to be fast, but it's going to be accurate. Oh, right, so the speed of the whole thing is basically entirely dependent on the segment count, right? And what I care about is how reasonable is the estimation of an arbitrary curve given only 1,000 segments. That's the thing I kind of care about that a lot, honestly. So if we do well, so the line, let's say this. Rough testing shows seg 1000 seems okay for lines. Try circles. Let's try circles next. Yeah. Okay, so the exact arc length of a circle is going to be the perimeter, which is pi times d. So if we do math pi times 40, okay, so we lose accuracy on the 4th decimal place there. Is that acceptable? I don't know. I think not. if we round it, right? So, well, it's still wrong, but it's way closer. Okay, so let's try seg 25. Yeah, Let's try that. Really? Okay. Let's turn rounding off here for a second. Yeah, so we're getting closer with a segment count of 5,000. We could do some kind of dispatch. Sorry, we could do some sort of conditional segment count thing, you know, because we're getting into slower millisecond times here, which I don't love. That's the thing. Let's go 4750. That's the wrong. Don't love that as a line of logic. I don't love that. So let's do this. Let's not worry over much about that. How about that? Let's go back to this. Okay, so we're rounding the 5th decimal place, and in that case we do get the right answer, right, for if we do this. Whoops. Right, if we round this, utilities to 5, we get the, ooh, it's different. Right, of course it is. So it's accurate up to, it's fairly accurate up to 4 decimal places, and we lose it there. I don't love that. Okay, well, let's do this. Let's say we need 10,000 segments as our accuracy. Let's assume that we need that, okay? I don't know that that's fair to assume, but let's kind of go with that logic for the time being. We're still not accurate there. What's going on? Let's see. It's very possible that we can't ever get to the right answer. No, we can. Okay. All right, so let's use this. We're slow here. Unfortunately, we're quite slow. But we're accurate to 5 decimal places. Okay. Here, are we accurate? No, we're not. Let's double this. We're just kind of finding happy bounds to get to here. Okay, so here, let's drop this down to 15 again. We're kind of finding an upper bound that we feel comfortable with. Let's try, oops, one like this. Okay. No, so we need 2. Well, no, sorry, let's do 1, 5. Let's try to get there. Okay, that's not it. 20, there we go. 120,000. Ooh, that's still wrong. 125,000. Let's go 30. Did I mess something up? I might have messed something up here. No. We're kind of easing into the right. There we go. Okay, so now let's try this. No, let's keep this like that. Let's use that as the happy circle calculation. We'll go with something like that. Okay. So now let's see what we can do. If we're given this segment count, the assumption I'm kind of using in my head is we're using a circle calculation. We know the exact to get the arc length of a circle. Okay, so that's easy. Easy enough, I should say. And we can use that to kind of tune things a little bit. What I want to do is kind of make the assumption that for any parametric thing, if it's based on straight line segments such as polyline or polygon, we can kind of get away with lower segment counts and not worry too much, because we're going to get pretty good, pretty decent estimates with the arc length calculation given the step sizes. Now the problem, but we don't even really have to worry about that, because we're not really going to use the arc length estimator function on straight line segment things, because those will have the length property built in and will have exact calculations. That's true for line, that will be true for polygon and polyline, so we're good with that. For circle, it's also exact, so we don't technically need it there. For ellipse, for arc, well, even for arc is actually, we can make it exact because it's just a percent based thing. Ellipse we can't, we have to estimate, and Bezier curves we have to estimate. So if we tune our estimator to get circles accurate within a certain decimal place value, 5 being, I think, sufficient for all of my use cases, then what's the point I'm leading to here? Then I'm just assuming that if a circle is reasonably accurate, then a Bezier curve will be sufficiently accurate in terms of its arc length, using the same parameters. So this segment number, I'm going to assume will be about approximately okay for Bezier curves. So, but now what I actually want to do is check A again, and if we look here, we're actually under my initial target goal of less than half a second. So already that's a huge improvement. I feel pretty good about that, but I want to see if I can make things better. And I want to see if I can make them better by learning how to use reducers. r/reduce function. I don't know if that'll actually make a difference. It hasn't. So we don't just get a free, we don't get anything for free here. I also wonder, this is not the solution, I'm just very curious what happens if I do this. It actually slows it down. So I made pmap is parallel map. You know, we might actually not get any improvements here. I wonder though, pmap curve might be where we get. Okay, so that actually did. Interesting. Okay. That is something useful. Here I'm wondering if I should learn either, one, figure out how reducers work, or two, figure out how to build a transducer. Because if I do reduce plus, oh, I thought that would return a transducer. No matter. I will be right back though. I have to check something. Whew, all right. All right, I got about half an hour left here. Let's see what I can do in terms of understanding and improving code and all of that good stuff, huh? Let's see what I can do. Okay, so this here PMAP curve does speed up, so let's think about that a little bit. See, the problem is I don't want to just use PMAP because I can't use that in Clojure script. Does this work in Clojure script, by the way? Let's see if I've got Eclipse REPL. Just use this as an example. I think this is effectively running Clojure script. Let's see. Well, okay, let's not. Adam, I don't know if this is. Oh, I have to. We'll have to. I want to fix that. It's not it. I want to improve those two. Got a lot of stuff that I keep not doing. Oops. Let's try Clojure.core.reducers. Maybe this is the wrong way to go. Try something else. I'm going on a bit of a tangent here, but you know, that's fine. Let's try this. Oh no, it didn't work. It copied one incorrect element. This should work. Alright, so literally all I'm trying to do is get a... So Node Babashka should effectively be running a Clojure script environment. Okay, so let's try require clojure.core.reducers as our shoot. Okay, well this might be a non-starter for me because I don't think okay, so it does have transducers. So here's what's going on in my head. I'm pretty sure the reason to use Clojure core reducers, I think the reason it ends up speeding things up is because it does like PMAP, parallel map, and stuff like that, and I don't think there is necessarily an equivalent namespace in Clojure script. Oh, I have to search all of GitHub, please. I find this search function a little bit annoying sometimes, to be honest. Okay. Well, okay. List of Clojure script core namespaces. Let's go with that. No. Clojure script namespaces. No, this is also not what I'm... Okay. Well, Clojure core reducers. Clojure script. Let's see, let's search this repo for reducer. So it does have reducers. I'm a little, okay. Really, I'm kind of doing this in a backwards way, aren't I? Maybe... can I use our fold in Clojure script? It is here. Okay. Right, so here, performing operations in parallel is currently not implemented. That makes sense in the Clojure script context because it's single-threaded, so it kind of doesn't matter. I guess that kind of means this approach is a bit of a non-starter. So maybe I won't worry about it. What does seem useful though, right, is the idea of converting my map reduce multiple steps thing. Maybe I can turn it into, well, first of all, maybe I do still get improvements even if I don't parallelize anything, because I'm pretty sure the only element that's parallelizable, or the only part where parallel stuff happens, is fold anyway. So perhaps it's still worth doing because maybe I get some performance improvements anyway. But now I am kind of just wondering if is there a search for not really. Well, where's the transducer? Let's see, is transduce, it is in the core. Okay. So let's go over here. Let's do CLJS core, and we'll see if transduce is in here. So Command F, transduce. It is. Okay, so here we go. So I kind of wonder if I use the reducer's namespace to build a different structure to my arc length pipeline, if it ends up being logically equivalent or nearly logically equivalent to just using some kind of transduce. So what I want to do is figure out how to build a transducer. Either way, I need to understand, for myself, I want to understand both of these things eventually, because I feel like they are kind of the same, but might have subtle differences, and I just don't know. That's the truth, is I don't know. So let's try to figure out how to build a transducer. And then using that, we could maybe figure out a prototypical arc length calculation that is an improvement over what I've got implemented already. One thing I'm super happy about is, without even changing the arc length calculation, I was able to build a fastline tool here to speed up my Bezier arc length. So if I time arc length proto of A, it's under my original goal. So it used to be, but when I was starting this today, it was around 2 seconds, and now it's 0.4 seconds. So 0.5 seconds if I round up. So that's a 4 times improvement, which is pretty good, gotta say. And you know what? I'm gonna call this a pretty decent estimate. And I'm gonna assume it's pretty decent because, well, it's using a fairly tight segment size. So I'm gonna be happy with that for the time being as a good win. But I do want to figure out how to kind of lump this all together in a nicer way. Oh shoot, there's of course the problem of this. That's okay. Oh, well, it got faster again. Got rid of the PMAP, which wouldn't have worked anyway. So that's good. Let's copy this. So far, definitively. Oops, that's not what I meant to do at all. Copy this, please. There. Okay. Oh, this. We, of course, do have to do this. Okay. Right, so now timing arc length proto is 3.3 seconds, right? Am I? Yeah. and arc length should be almost exactly the same. So we got 0.3 again. So we're totally in an improved state already, which I'm very happy about. I did that actually, I want to say probably around 45 minutes in, I got that improvement already. I've just been kind of spinning my wheels experimenting otherwise. So like, that's pretty good, I gotta say. Let's see what transduce gives us here. Let's kind of figure out how to do this. Okay, so here's what I think is happening in this case. We're given an infinite range as the input to sum. But before I sum them together, I'm actually running the xf over each of the appropriate inputs, which could be anything. So whatever gets input into here, take 10 makes sense from an infinite range. You can take 10 and then filter out odd. So you run that single function over what's coming in, and then you're adding them together. So this is equivalent to doing plus on a list of 5 odd numbers or 10 odd numbers. Sorry, let me, if I take the first, if I filter odd from the first 10, which I'm just gonna take 10 from range, and if I do reduce plus on that, it's not going to equal 100, it's 25. So it's running slightly differently. Oh, comp. This returns a function filter odd, I guess, and so does take 10. That should work, right? Yeah, so if I transduce xf on range, wrong number of args 2 passed to transduce. How many arguments are required? Transform, and then the function, then the collection. Oops. Okay, so let me just work through. Can I identity? What happens if I do identity? 0 args pass to identity. count that is 10 numbers, right? Because it's take 10. Take 10 of the odd numbers. That's what the XF is doing. Boy, okay. I also realized okay, good. Well, let's literally try to reverse this whole thing. So let's do sure. But we actually want to def that comp. We want to comp things in reverse order. And we'll just comp these things together. And then run it through range with plus instead. So let's try that. Let's see if we can get that working. Okay, so the first thing we want to do is actually comp map apply utils distance. Okay, that's the first thing. Partition that 2 by 1 and map curve. Okay, is that a valid? Ooh, it's not valid. Of course, we have to do it this way. We gotta wrap it like this. So given a curve, I want to return the composition of this. Okay, so that should work. Okay, so given that, I mean, let's figure out if this works. Why don't we? Let's go here and we'll do transduce. Okay, so let's look at this as the. So what I want to do is transduce over the provided range. So in fact, what this should actually look like, let's start with the same construction here. Take this, pop that in there as a start. Okay, so we're building the range of segment values, which is easy enough. And we want to run that through the result of transduce with ALXF. Oh, we should make this private, shouldn't we? Yeah, I think that makes sense. Okay, so the arc length transducer function requires the curve as an input because that's comped into there. So we'll transduce that whole thing with plus to reduce it like I've done based on this example here. Sum them, transduce given the comp function, and plus to group it all together. We know that we're doing a reduce on this anyway, so let's transduce it with plus and see if that works. Maybe. I mean, it worked, but it didn't seem to actually save any time. Although I gotta say, I'm pretty pleased that that did work pretty much the way I expected it to. Let me see here if I conj it. Oh, let's also do this so it's way smaller. Ah, I made a mistake. Let's undo this. So this might not actually have worked. Let's try it again. I was timing the wrong thing. Let's try proto. Ah, shoot. Okay, well that's fine. Let's try to figure it out. Well, first of all, let's do ALXF, right? Let's give a curve A. Okay, so this is a comp function. Good. Oops. Well, okay, let's back to the drawing board. Let's take this. Maybe I did the order incorrectly. Maybe this has to be inverted. I don't think that's right, but let's try it. I think that's wrong, but nevertheless, let's give it a shot. No. Okay, well, let's reduce this to a simpler, let's try this. Let's do map curve. Okay, I don't think this is going to be right, but let's give it a shot. Okay, so let's figure out transduce ALXF2, but we can't do plus, that won't work. Let's try Clojure. Okay, so we do get something out of this, so that's good. Great. That's not so bad, actually. Let's now figure out what's gone wrong. Okay, okay. We're actually getting somewhere here. I like that. Let's compose that. I mean, let's try this. Partition 2 by 1. Let's try that. Okay. So there we go. We're getting into problems there. Why would that be? Well, okay, fine. Let's just sanity check this. This should also not work. I just want to double check. Null. That's different. Okay. Oh, okay, I think I'm gonna go soon, but I was kind of hoping to figure this one out, honestly. Let's see, what am I not understanding? Okay, so it seems like the transform ends up being filter odd and then take 10. Okay, so let's think about it that way for a minute. We want to put in, so we get a range, it does this and then it does that. So it's in sequential order. So maybe I do have to. So this should be correct. Why does this end up being null? That's what's going that's what's going through my head. It's possible maybe I have to make this partial. That's possible. Partial. Let's see. Maybe that's helpful. Not quite. Wait a minute, maybe it's just... Okay. This isn't gonna be right, but let's give it a shot. Alright, I don't understand it, so let's see if there's other things we can do here. Unfortunately, I might not be smart enough to get this right now. Might have to be something I do late while not streaming. In fact, I think I am gonna get going now. I've actually had a pretty good stream. It was very focused on just one function and trying to optimize and understand it a little better. But nevertheless, I feel quite good about that. I think it's sometimes progress doesn't appear to be that eventful, but nevertheless I feel really good about what I've done so far. Yeah, that's really all I've got to say. This feels like this here, arc length, if I do, let's go back up to time. Arc length A, we're under 2 seconds. We're under 1 second even, which is quite good. So that's a huge win already, because what it means is, first let me go over here and redo bez like that. There we go. Okay. So what that means, okay, is even doing this. Oh, actually, wait 1 second. Okay, good. Yeah, so if I def B bezier that was pretty quick. So then if I do, that's pretty good. Gotta say, I feel pretty good about that. So let's do show parametric. Oh, it's in Scratch. This one was way slower, interestingly. But I think I'll be okay with that. That's kind of fine, honestly. anyway, I think that's pretty good. I am fairly happy with that. Oh, let's do one final thing, actually. Let's def C is a bezier with points that go 0, 0, 20, 20, 40, 40, 100, 100. Okay, so it's a straight line. In fact, let's make it literally a straight line along the x-axis. So we know that its total length is 100. See that? Okay, good. I'm happy with that. Reasonable accuracy for straight line segments. It's obviously going to vary, but I'm quite pleased with that. So that is good enough for now. I'm going to do a bit of transducer learning off stream, and I should be back on Thursday and hopefully streaming on both Thursday and Friday. So thanks everyone. That's all I got. Bye-bye.